Hello everyone, and welcome to the 6th episode of Iron Bill. This episode is going to be recorded under extreme circumstances because, as you can see, my headphones and with them my microphone has died, so we're going to record this one without a microphone. Hopefully you hear me all right, so if you cannot hear anything, then please scream in the comments so that I can maybe fix it, but well, hopefully my power of telepathy is enough to get my voice out there. Okay, so let's get started, because today we actually have a pretty exciting topic to talk about. Today we're going to talk about Zig and Rust and why Targetall as a code base choose to use Zig as an implementation language. To kind of like maybe cool someone off, I'm not going to tell that, hey, kind of like Rust is a bad language and everyone needs to learn Zig immediately, because, well, that is flatly not true. Like, Rust is an awesome language. This is the language I have personally used professionally for most of my career as a professional software developer, and I would say that, like, in general, kind of like just use Rust. It's like awesome language. But you know, when you need to pick a particular programming language, what really matters is the context, because there is no like better or worse languages. Really, everything is only makes sense in a particular context. And in the context of Targetall, I would argue that both Rust and Zig are reasonable choices, and probably Zig actually has an edge here. So I would say that one could write Targetall either in Zig or in Rust, but Zig probably makes somewhat more sense. Okay, and actually, if you have been watching this series from the beginning, you understand quite a bit about the context of Targetall. So probably you should understand why Zig. So just one moment, it looks like I might be clipping my volume because I see the microphone go into red, so let me make myself a little bit quieter. Okay, so hopefully now I'm not going to get volume clipped, and hopefully you still can hear me correctly. Again, apologies for technical inconveniences. Okay, so let's actually, as usual, dive straight to the code. But actually today we are not going to have too much code, we mostly will be like, again, hand waving and philosophizing about programming languages. But it's important to like go back to some of the previous episodes and recall that last time we talked about how Targetable has static limits on any kind of a resource, which leads to static limit on like the main resource memory, which leads to this particular code pattern where Targetable allocates dynamic memory only during startup, and after a startup, it just basically never ever calls map or memory map or whatever. So that's kind of like one important thing from the first episode. And from the episode before that, we were talking about how Targetable is highly concurrent but a single-threaded code base. And kind of like these two things, single-threadedness and no dynamic memory allocation, explain a lot about like why Zig and not Rust. So let's actually dive a little bit deeper here and draw some diagrams. No, I don't want this to be green. I want this to be like, you know, just without any kind of. Okay. Yeah. So kind of like the elephant in the room when discussing Rust is the memory safety, because the purpose of Rust language is to give you systems programming, to give you programming without an allocator with like very low level access to resources, which nevertheless maintains memory safety. And to like discuss why not Rust, why memory unsafe language, we need to like discuss what is memory safety. And kind of like abstractly, memory safety is like pretty important thing, because if your language is not memory safe, then it opens up your code to pretty terrible exploitation avenues like remote code execution and whatnot, which generally is something you don't want to have in your code. So kind of like basically the idea behind memory safety is that not all bugs are equal. There are bugs which just lead to your program crashing, and that is of course unfortunate, but it usually isn't the end of the world, because if the program crashes, you just go and restart, and like maybe you lose some work, but like again, it's not like you like lose money or something. But with memory safety bugs, it usually is the case that program doesn't actually crash, but rather exhibits some undefined behavior, which might lead to more severe consequences than program just not working. So, for example, a memory safety issue might lead to remote code execution, where instead of crashing, your program starts executing some arbitrary code of an attacker. Or memory safety could lead to issues where you leak your private data. So you kind of like connect to some server, and instead of sending to it an HTTP request with the data you want to, you like maybe send like your random RAM, which might contain your private keys or whatnot. So that's kind of like the idea behind memory safety, that we want to limit the consequences of bugs. And when speaking about memory safety, a useful like mental tool is to classify memory safety issues into spatial, or related to like space, and temporal, related to time. This is kind of like very fuzzy classification. This isn't kind of like super rigorous definition. It's in general kind of like rigorously defining what memory safety is kind of like challenging, because like if you really dive deep into that, you kind of like end up in a situation where you say kind of like memory safety is like what I'm saying it is. Like basically memory safety is what like when my formal model of the language gets stuck, where like there is no like formal step and a small step or like big step in recursion semantics from language. So this kind of like nesting. But the practical intuition is useful. So what are we seeing here on the screen? Some of you might say that that is a rectangle, but that's actually not it. That is like memory of our program. So, and it's kind of like the important thing is that it's actually linear. So, like, kind of like it looks like two-dimensional, but actually it's like one-dimensional, where like this is like just like zero address, and this is like some like huge address like 0xFF, and like a lot of more set bytes here. And from the perspective of the hardware, like memory is basically just kind of like a bag of bytes. When you are programming, though, you like to subdivide your memory into objects. So, kind of like you like to say, hey, this region of memory is actually not just memory, but like something like struct foo. Sorry, I have a horrible handwriting, and if I try to handwrite using my mouse, my handwriting is like double plus horrible. So it's like struct foo. Okay, and kind of like the catch here is that all these structs tend to be collocated in the same linear address space. So although physically there is no I can actually type here, that is so much better. Yeah, so that's kind of like the change. The underlying memory is untyped, then we, as a programming language, add some structure to it. We say, hey, those bytes over here are not just like bytes, this is like our foo, or like our person, our spam object. And the challenge of memory safety is basically not getting into a program state where there is confusion about what a particular address memory stores. And let's look at the two kinds of things which can go wrong: temporal and spatial memory safety errors. So let's look at the special one. I don't know actually how to pronounce it. Never mind. So let's say that this is actually our like pointer to foo. So this is our like const star foo. I don't remember in which order the constant struct goes together. Anyway, so that's kind of like we have struct memory, we have like pointer which points to struct, and a special memory error goes if you like use this point and like try to access this like object foo, and you actually miss, and we kind of like access bar or like access something part in between the two. So this is like special error. Like there is an object, it is in memory, it is there. We have like a pointer to it, but for some reason like our pointer like misses, goes out of bounds. So that is like your classical index out of bounds error, where you have an array of objects and you access like element which is past the end of the array, and that is just like some random memory, and that's not really great. The good thing about these spatial memory errors is that they are pretty easy to catch. So the idea here is that every time you access a particular object, you actually go and physically check that the bytes you are reading are within the extent of the object. So most of it, and this is like just basically it's value checking. So when you have an array and you go and read an element of an array, you first want to check that this is indeed in bounds, and if it is not in bounds, you crash. And that's kind of like the thing. It's like memory safety isn't necessarily preventing all out of bounds accesses. It is just preventing out of bounds accesses from reading arbitrary memory. It is like elevating arbitrary runaway read or write into an actual program crash. So yeah, that was like spatial memory safety. What about temporal memory safety? So the target situation is the same. We kind of like have this object, have this pointer, and then we miss an object. But we miss it not in this way, but rather due to time. So this is a picture at some point in time. And then later, someone actually goes and deletes this object foo, and maybe allocates a related object, I don't know, let's make it orange, allocates an object, and that's like actually some completely different type, like struct quacks, and maybe it is even like, you know, to make sure that it's like, can I actually extend this? Yeah, like actually it is like much bigger, because well, it's like object of a different type, so like memory completely different. But we still have this outdated pointer, like green pointer, which at some point in time before was pointing to object foo. And then if we use this pointer right now to access this memory, we actually will be accessing object of another type. And that's again going to be bad, because the meaning of bytes now at this pointer is completely different, and that can lead to all kinds of undefined behavior, because again, kind of like maybe in that maybe what this foo is actually a function pointer or an object with a function pointer. For example, maybe this is an interface, and this is like a table, virtual table of like addresses of like functions on this interface. And then actually, if there is something different there, then when we try to invoke this function by pointer, we are going to jump to some arbitrary address, and that's going to be arbitrary code execution, and that's pretty bad. And yeah, that's like temporal memory safety issues. And the second here is that spatial, usually I'm some self-conscious that my pronunciation is not super great, so let's actually spell it out spatial from space, and the temporal from time. Okay, so that's it. When I say spatial, I mean like this word and not like special. They're actually like not special at all, because they're actually like pretty common everywhere. Okay, let's go back to our data. Yeah, so the difference between temporal and spatial ones is that while spatial are very easy to catch, you just do bounds checking, temporal are like really annoying. Like so far, people don't really have like any good way to catch temporal. Well, until very recently, people didn't have a good way to catch temporal memory safety issues. So right now, we actually have two pretty interesting techniques. One is that cherry architecture for CPUs, where we add some hardware support for caching temporal memory safety. And that's great, but that requires some special hardware. And on the other hand, we have Rust. And kind of like the trick that Rust pulls is that it kind of like realizes that tracking temporal memory safety is kind of like hard. But what is like the reason why it's hard is the problem of aliasing. It's a problem of having several pointers to actually, okay. Let me if you're drawing pretty pictures, let me actually draw an aliasing pictorially here. So yeah, so aliasing is like basically a situation like this, where you have two pointers, and one of them isn't, and when you have more than one pointer to an object, and one of those pointers is mutable, that's kind of like aliasing, and that thing makes computing any kind of static analysis really challenging. So the idea behind Rust is that, okay, let's track aliasing in type system, and because we are tracking aliasing in type system, we actually can track a lot of other properties, and in particular, we can prevent temporal memory safety issues. So that's kind of like the big benefit that Rust gives you. It gives you memory safety through static analysis. Let's be more precise here. Rust gives you special memory safety through bounce checking, and it gives you temporal memory safety through static analysis. How does it relate to Zig and TidyBuild? Well, if you recall, in TidyBuild, we do static memory allocation. Well, static kind of like it's static. Some might object that we don't actually do static memory allocation because, well, we don't allocate memory in like data section of an L file. Rather, we allocate memory at the startup. So we do call malloc. But the trick is that we call malloc at the startup, and we call malloc with a specially computed bounds, so we know exactly how many objects of each type do we need, and then we can don't allocate anything else. And kind of like we call that like static memory allocation, because kind of the idea here is not that you allocate at a particular time, but rather the idea is that you know precisely how many objects do you need, and you allocate exactly that. Okay, anyway, so we have like this static memory allocation. And that means that in the heap for TidyBuild, once we kind of like slice the heap into like throughs and bars, they are not going to change. So we, at the startup, we sliced our heap, we said, hey, this is a hash map, and like this is an array, and this is like another array, and this is like a struct of arrays. But after that, that's it. The picture remains fixed until the death of the process. And that means that kind of like if you have a pointer to something at some point in time, it's generally going to stay valid for like forever, because this struct foo is never going to move from under your feet. And that is kind of like one of the biggest reasons why Rust is not a big benefit for TidyBuild. So again, this is kind of like one of like the arguments I'm going to present today, is that Rust helps you to track temporal memory safety very effectively. But if in your code base you don't have a lot of temporal memory safety problems, because your objects are actually living forever and they're never moving in the heap, then you don't get a lot of benefits from this tracking. Again, this is not to say that like temporal memory safety is completely non-issue. That is not true. So let's write a simple code, for example. So for example, kind of like if we write something like this, fmbed, which returns a pointer to an int, but the actual pointer it returns is like a pointer to a local variable. Well, that's going to blow up. This is going to be a temporal memory safety issue if we call this function then access resulting pointer, because, well, the objects on the stack don't actually have this static lifetime. Well, actually I realized, okay, so before that I was talking about how some might object that like static isn't actually static. Well, I guess in our defense we could say that we use static in precisely the same sense that Rust uses static lifetime. Because there is like box link function in Rust which returns you a static reference to something which was allocated. So that's kind of like the meaning of static we use in TidyBuild. Like all our memory is static because we actually we kind of deallocate it, but at the very end when the program crashes, and arguably we might even not need to do it, we can just like crash and let the operating system to clean up memory for us. Anyway, So this is a temporal, also temporal memory safety issue because, well, when this function returns, then the x variable is no longer there. It used to be on the stack, but now it is not. Now it is like some garbage. And these issues could happen in Zig. They can't happen in Rust. But those are actually kind of like a minor fraction of problems in comparison to like your objects in a heap, changing their addresses or having complex lifetimes and relationships, and that part is solved. So again, let's go to white variable and say that we kind of like basically want to manipulate our code of Zig. And one thing here is that I have like everything has static lifetime, which follows from 28, no, dynamic memory allocation. So yeah, that kind of one half of the puzzle. The other half of the puzzle is that we are single-threaded. So another kind of like temporal issues you could see in the code base is when you try to access something from the two threads at the same time without incurring necessary synchronization, which is also undefined behavior. And this is also a big benefit to Rust, or probably like if you are not a system programmer, if your language of choice is something like Go or Java, that is actually like the biggest benefit of Rust for you, that Rust tracks thread safety. Rust allows you to write non-thread safe code, but at the same time be rest assured that you cannot actually accidentally use this non-thread safe code from multiple threads. Again, this is something we don't have as a problem in Trivial because our code is single-threaded. And the combination of the two, the fact that we write single-threaded code and the fact that we do static memory allocation, actually significantly reduces the benefit that Rust safety checks bring to the table. By no means I'm saying that because we don't do dynamic memory allocation, we're like completely safe. No, that's like patently not true. One example is that this kind of like returning pointer to the stack variable, which is kind of like we could hit in tiny middle. Another like next example where like you could hit memory safety issues is if you have something like this. If you have const tricky, which is m, which might be either a string or a number. Well, actually, string number. Yeah, I think that's it. And what you could do here is that, let's say we have a pointer to this thing, and you take a reference to a field of this object. So again, this is a reference to a field. It is not like a copy of this slice. And then you're going to go and say that, hey, actually, my t is now a number. And then you go and access something from this reference. And this is also kind of like a memory safety issue, which is not prevented by the fact that like we don't do dynamic memory allocation and that like Zig does not checking, because here is also kind of type confusion because we think that the memory that R points to is a string, while in fact it is actually a number right now, and kind of when you try to reference it, we get some garbage. Because probably, I don't know what's the layout of slices in Zig is, whether the first element is a length or a pointer, but like for example, if it's a pointer, right now we're going to dereference pointer with a numeric value of 92, which is definitely not good. So yeah, those issues are kind of still possible in Zig. They are far less frequent than your run-of-the-mill memory safety vulnerability in the C code base, where you do like PAVAC and then you do free and then you do free again, because, well, why don't you like double free something? And that is because kind of like this residual is not that frequent. We are actually not getting that much benefit from additional Rust checks. This kind of like this is like one part. Then there is, okay, so let's actually group this together. So Zig, everything has threaded lifetime, has static lifetime, and then we are single threaded. Let's actually group, okay, this is a complex one, so we're going to group this into like two areas, like Y not Rust, like YZ. And here is like code free, everything has static lifetime, and then where is like single threaded? Yeah, I'm like 24 single threaded. Okay. So again, I guess yeah, I realized that I forgot like one super duper important aspect of Rust memory safety. So kind of like yeah, like Rust is a tool for like catching these kinds of errors, and that is kind of like only half of the magic for us. The kind of like big thing about Rust is that I don't know, when you write something, I guess what would be some substring function? Okay, yes, let's say find. We have like haystack as a string, and then we have like middle, which is also a string. And what the function returns is the first occurrence of middle in the haystack. And the magic of Rust here is that you specify like time relationships in the signature. So kind of like not only Rust checks that like whenever you use this function is going to be safe, but it actually requires you to type out the signature, which tells the reader and the compiler the exact relationships between lifetime parameters, which right here says that this function will return a pointer to the same memory, but haystack is pointed at another memory which is pointed to by the needle. And this is huge. This is kind of like the big idea about Rust, that it allows you to express memory safety in composable way. That in turn means you can safely combine multiple libraries written in Rust. So kind of like not only the language is able to kind of like check the code base holistically, run some global analysis, which Rust doesn't do. Rather, what language does is that it allows you to write like your code base as like 1,000 separate tiny libraries, integrate those together, and then check that the integration works. And this is like really great for code reviews. But actually, if we go back to, do we have something about dependencies? Okay, we have like something for building long term, but actually, I think we would haven't mentioned this before, but let's do this now. One property of Triangle is that we don't have dependencies. Well, it's not true that we don't have dependencies. We certainly depend on Zig. We certainly depend on the Linux kernel for I/O urine. But what we don't have is we don't have like arbitrary library dependencies where we pull someone else's code from GitHub, and this goes back to like our desire to build for long term, because again, kind of like the rule of thumb here is that kind of like the bigger your project is, the more long-lived your project is, then the less benefit you get from dependencies. Like at some point in the lifetime of your project, it becomes simply cheaper and faster to write the thing yourself in a way that you control, in the way you know ins and outs, than trying to coerce someone else's code to fit into your particular requirements. So kind of like dependencies are this like tricky time-saving things where you need to be like very cognizant about like whether you're going to put something at the core of your project or is it just like a help. Because if something is a core of your project, then it makes sense for you to own it. And for Tricapital, we want to really narrowly scope all the stuff we do, so that, for example, we don't need HTTP parser, we don't need some like complex protocols, complex file formats. We kind of like do everything from scratch, so we don't like have a lot of necessity to use dependencies, and we can like build everything from scratch, which allows us like, over a long time to actually build software faster and in a more reliable way. So again, I think we should have covered this before, but yeah, probably like in the first lecture. Anyway, so yeah, kind of like we don't have dependencies, and that means that we also don't need to solve this composability of different pieces of code in a safe way problem. We kind of like could say that, hey, the rule in Tricapital is that we only do static memory allocation. We never allocate memory after startup, and that is the rule which is uniformly followed by all the code we have, and we don't have to enforce this rule across organizational boundaries. We don't need to make different teams of people to agree to these rules. So this is also kind of like the reason why Rust doesn't really bring a lot of benefits for our use case. And again, kind of again, this is probably going to be longer than an hour. This is like a very deep topic. And again, I'm not saying like this that Rust is bad due to all of these things. No, every single of these things would actually be a benefit in our code base in isolation if it didn't come with like associated costs or opportunity costs. Rather, I am seeing that the benefit of these things is rather less important in our specific context. Okay, this is problem 34. And at this point, like maybe one okay, so kind of like why if you don't do Rust, like why what's the benefit of Zig? And there are a few, but those are actually kind of like hard hidden and pretty significant. So the biggest benefit of Zig is that it's just like simplicity. And like simplicity is like really kind of like undervalued thing in software development. Like I mean, like everyone literally all the time tells how like the code should be simple, and kind of like the simplicity is very important. It's like a common concept in like our like general mythology of software engineering, but it also is like almost non-existent in real software. Like, real software becomes complex for essential or accidental reasons, like really, really fast. And the only way to get simplicity is to kind of like aggressively like swim uphill, aggressively battle complexity, because kind of like the default state of the things is complexity. Simplicity like means like really, it's not like not only simplicity means design. Simplicity means like continue to design, and like any help you could get from tools to ensure simplicity, you should use. And kind of like, yeah, Zig chooses not to achieve safety via the mechanisms that Rust uses to, because Rust uses like really complicated mechanisms. It's not only like borrow checker, like Rust's safety story very fundamentally depends on its generic implementation, its generics implementation. It very fundamentally depends on LLVM being able to optimize away zero cost abstractions. So kind of like Rust expresses safety, but expressing the safety requires like a ton of language machinery. While in Zig is kind of like really while kind of like Zig gives you the ability to write the source code which gives you the same machine code, but at the same time the source level semantics is like much simpler. You don't have like these towers or abstractions where kind of you can in Rust like the old school types like full, which is a parameterized like bar, which is a parameterized bars, or like something like that. Like with the kind of common keys, like for example something like pin, because like pin is always like pin, which pins a pointer, which actually points to your future, which might itself be parameterized by like some state or whatever. So yeah, this tower of abstractions in Rust exists primarily to enforce memory safety, and kind of like at runtime it kind of doesn't really cost you anything, because like at runtime it's just like the very innermost full, and kind of that would be like probably of course it would be then on you to check that you use this thing correctly. In some cases, again, Zig is very helpful. Zig is much more helpful than C in detecting various problems, like for example overflow. If you compile and release safe is defined behavior, there is like balance checking, and there is like this special undefined value which integrates well with sanitizer, so that if you do hit a bug, then you like immediately know what's going on. So kind of Zig is much safer than C. Still kind of like it's not Rust, but if you achieve this safety through other means, like for example doing static memory allocation and doing extensive testing, then you could reap a lot of benefits from simplicity. And kind of like Zig's code is like really simple. So kind of if you look at like something like replica on prepare, you really see that kind of like there's nothing particularly highbrow around this code. There's like really no abstractions, no kind of like, hey, we're doing like this abstract operation which is parameterized at compile time, that is straight, whatever. Just like very simple, very procedural code, and that's kind of like, to be honest, like the biggest reason why is it. But that's also kind of like not super satisfying, because like simplicity is always like hard to discuss. But there are a couple of like more hard and crisp reasons for Zig, and one is that is like comp time, because well, kind of like again, if we look at message pool, non-last pool, where we allocate messages, we have like this awesome computation of like, hey, how many messages do we need, and that is like all done at comp time. Like you could do this same thing in Zig, in Rust, but it's like going to kind of like look significantly more uglier, because well, everything is going to be like screaming snake case here. We want to be able to use all the control flow structures here, so that we don't need loop here, but kind of like still. And if you look at something like, what do we have a full set? Somewhere here, yeah. So we have like things like computer fixed point iteration loops at comp time, which might be challenging for like if you have like actually okay I think it's actually not true. Actually, you could pretty okay because yeah, if this were in iterator, then you wouldn't be able to write this in today's Rust. But okay, this is a simple while loop, and okay, this is actually interesting. Maybe I will enter here. Maybe all those constants could be there because I'm actually I want to find something like some non-trivial example of computation of a constant in particular, which is going to be challenging in current class. Probably, yeah, probably today actually you could compute most of these things in Rust without too much problem. Well, yeah, okay, maybe actually like this particular aspect of comp time is not really really good argument. What else? Well, there is like this kind of like hard hidden there is a kind of like, let me show you something more. Something more interesting, yeah, which kind of like goes to, let's be fair, let's see, okay. So this to V2. So the big thing, which like is slightly more challenging in Rust, is like control over layout. Basically, kind of like getting each bit and byte in the data structure to be exactly where it needs to be. So, for example, here we look at the no pattern function, which actually goes and checks that whatever type we have here doesn't have interior pattern. And this is a function which is called a lot in trivial. As you see, it's like basically every data structure, every significant data structure which we have here is going to have this no pattern. Why is it? Well, because that is a property of trivial that we kind of like do zero copy parsing, that we kind of like don't read bytes from disk or from network and then parse them into our internal structures. We rather use those bytes as is for both simplicity and performance reasons. And that means that like you need, like, for example, ensure that you don't have a pattern in your data structures, because if you have pattern there, then the actual layout on disk or in the network is going to be non-deterministic, and that's can hide some nasty problems. Like, for example, if your data structure on disk has pattern, that means that when you read this data from disk, you also read the pattern. And if before you read the thing from disk, something else was written at the offset, that data from that something else is going to end up in your pattern. That actually might be a logical problem similar to memory safety issues. So again, kind of like technically there is no memory safety, but there is like this poison data, something which potentially was like private before, which now resides in your memory, simply because you kind of like didn't account for invisible data, you didn't account for pipe. So kind of like we worry about those things in Zig, and like we just like need to go and check the type is not that, and you kind of like can do this in Rust, but it's going to be like extremely ugly because you cannot just like go and reflect on the type and compute all the offsets and check if there is no pattern. So okay, kind of like let's actually split this. So comp time for static limits, and Rust can do most of this today. But then we have like comp time for data structures. Rust can do this, but it's like very challenging. And hybrid code and like not baby code. Like you really kind of like you need to go deep into like proc macros and like traits and whatever to make this work. So kind of like as another interesting example of like this comp time for data structures for assertions in TypeBuilder, we like often need to compare types for equality, and kind of like if you think about how partial equality works, like in Rust, it's actually going to like compare fields, field by field, and have like this all order returns there, and that's kind of like non-optimal. If you're doing this in assert and you actually expect things to be equal, you kind of like want to have fast vectorized implementation. And again, Zig's ability to like reflect at compile time on data structures allows you to just like go and write this code without like thinking about this much. So you take you take a type, you take your pointers, then you kind of like find a big enough integer which fits alignment of this type, and then you cast things to slices, and then you iterate with all of them, and like you're done. So here let's actually add some examples here. So examples here would be like padding, bytes as slice, equal bytes. So those things, like again, if you should try hard in Rust to do them, but like you need to try hard. Like in Zig, you just go and write them. Okay, so I guess one thing I kind of like don't want to show is that I want to show, but I don't want to count this as like a super positive argument for Zig, is that sometimes we use like pretty kind of like significant comp time trickery. So for example, if you look at our state machine, and if you look at our groove type, it's going to be like a lot of comp time, because that's kind of like essentially an implementation of object relational mapper, because kind of like we create this like groove type, pass it this like a lot of comp time parameters, and then this thing goes and creates an object with fields corresponding to where actually is returned here. Fields should be fields. Where are fields? Okay, yeah. For example, index fields. Yeah, here it is. So, for example, we at compile time reflect on the objects passed to the groove, reflect on the requested indexes, and kind of like at compile time, create a struct, which has corresponding indexes for all of the fields. So that's kind of like content trickery. It's not kind of like the core part of like Tiger. Well, it's kind of the core part, but it's not kind of like super Tiger style. It's kind of like we do this because we kind of like can do this because Zig allows that, but that's kind of like not really why we are at kind of like the comp time can do pretty like complex things, but that's kind of like that's not really big benefit here. The big benefit here is that it can do simple things in a simple way. So, for example, if you at some point realize that hey, I kind of like want to compare type using first code, you just like write this down, very kind of like simple, direct first order code, and then it works, and that you don't need to think about like, hey, I need to write a pile of traits here and publish this trace.io because I'll no way I can like understand this code when I come back to it later. Okay. So actually, let me replace repeat simplicity several times with like simplicity is like where it really is at. And kind of like the final big thing about Zig is how do you say affinity towards cognizant allocations. Affinity towards no allocation. That's again a big thing. That's something we looked at last time. Let's go back to client replies. Where if you, well, that was a client session, I think. Yeah, let's go back to client sessions where we had this kind of pretty magical thing where we take a hash map, this is a hash map, and we allocate this hash map, and we are not parameterizing hash map by allocator. We kind of like pass the allocator in the constructor, and then we don't have an allocator where the structure is actually used, so we get a static guarantee that this thing cannot allocate. This is API which is used throughout Zig, and this matches perfectly to us not doing static memory allocation. For Rust, that's not true. Rust kind of like generally, like if we speak about libala or std, where you actually have an allocator, Rust generally assumes that either there is a global allocator or otherwise that a struct carries a copy of an allocator. So again, you could express a similar API in Rust. You could write code which uses allocator during initialization, but then doesn't use it. But you won't be able to reuse existing collections, like for example hash brown, unless you go and kind of like wrap that collection into your own type, which takes this ambient global allocator API and kind of like just hides the parts which can allocate. Then again, it's kind of like absence of fundamental simplicity, because you take an API which has a wrong shape, and instead of like making it the right shape, you kind of like paper over deficiencies. So kind of like you kind of really try to mend it so that it like fits your code base. And again, that's something you could do, but in Zig, well, kind of like the way the code is written is naturally a good fit for the kind of code we are writing. So let's actually, okay, yeah, let's actually make it simple. So like non-global allocator. Non-global allocator means that there is an allocator, but it is not global. You need to pass it everywhere as a parameter. Okay, so I think that basically covers this. This basically covers Zig versus Rust. So let's sum up. Well, first of all, kind of both languages are pretty, well, not pretty exciting, but extremely exciting. Rust is a revolution. Rust changed the landscape of systems programming languages forever, and it is like the first significant change since like C conquered the world together with Unix. I guess maybe one can argue that Java was a comparable revolution because Java showed you that a lot of like code which people were thinking has to be written in kind of like system C programming languages can actually be written in a managed language. So Java was kind of like a proof that a managed language could really work in production. Right now, Rust is a proof that you could achieve memory safety without reaching for managed languages. So that's what Rust is exciting. Zig is exciting for a different reason. Zig is exciting because it really pushes this simplistic frontier. Like what Zig does with comp time is exciting, not because you could do some like fancy crazy things like we do with our groove type. No, Zig comp time is exciting because it simplifies the problem of like parametric polymorphism. That's basically kind of like how make code generic is something which like every language struggles with, because kind of like you could try to be Go or like early Java and say, hey, actually I don't want to, I don't think that generic is useful. We will be relying only on interfaces for polymorphism, and then you say, hey, actually no, I need generic, I need parametric polymorphism, and then you're in generics, and that kind of like your code becomes like crazy complicated, because if you look at some of the Java code bases with like all this like star extend super and like whatever, it's like really hard to reason about. If you look at more complicated Rust crates with all those type bounds, it's like really kind of like, it's harder to understand the signature of the method at times than to understand its implementation. And Zig shows kind of like a dramatically simpler way to write these kinds of software, and for this reason, this is kind of like exciting language which you should know about, even if you don't really need to use it in practice. And to be honest, I generally think that like probably you need Rust. Like the cases where Zig makes more sense than Rust, like to me, are not like very frequent. But well, they happen, and Zig is and Target is one of them. And kind of like the reason, and to reiterate, it doesn't mean that like Target couldn't be written in Rust. It could be written in Rust, but the benefits that Rust brings to the table are just not that important in a code base that is single-threaded, that does static memory allocation, that is very formally tested, because I'm sorry, this isn't scripted, so I don't have a plan, and that means that I might lose some very specific, very important points when I'm talking about it, and I just realized that I actually forgot one of like the biggest things here. And biggest thing, well, I'm kind of like talked a bit about it at the start, and I kind of like trailed away. So let's get back to memory safety. That the idea of memory safety is that it is not that we don't do bugs, but rather that when we do bugs, the consequences of those bugs are limited. So Tidal is a database. Like the reason why consequences of the bugs can be limited in general is because you always can restart your software, and when the software restarts, it's not a big deal because your software doesn't actually store the data. The data is stored in the database, and kind of like it's the database problem. That's kind of like the trick. One, like crash and restart is a very good property once you have like something else to delegate responsibility for like maintaining correctness, maintaining availability, Terminal is a database. Kind of like we still have this, hey, you could crash safely, you could restart safely, but this is not because we delegate to some other kind of thing. This is because we build this infrastructure ourselves. And there are some parts of our code which are absolutely critical in terms of correctness. Like if we mess something around our hash chain, for example, well, it's kind of like game over. The data becomes completely messed up. So for us, just kind of like crashing due to some memory safety issue, well, due to some issue which could have been memory safety, isn't kind of like really sufficient most of the time. We making sure that we don't have memory safety bugs is not enough for us. We really need to make sure that we don't have a lot of bugs at all. That we are correct software, which is very hard, which means that we put a lot of effort into correctness testing. And kind of like memory safety is a subset of the correctness testing. So kind of like the magic power of Rust is you could write a piece of software, you could write 0 tests, but then if you didn't use unsafe, you would actually be pretty sure that the result is like memory safe and it's not going to send random data to that record unless you have logical bugs. But again, logical bugs are less frequent than memory safety bugs in unsafe language and unsafe languages. But for us, we kind of care roughly equivalently about logical bugs and memory safety bugs, because we are a database for storing financial transactions. Anything, any bug there, anything which compromises correctness of data is very directly linked to some financial costs, some big financial costs. So for us, we need to ensure that we have testing methodology that we have our development processes geared at not making bugs. So while we could get some extra mileage of ensuring just memory safety, that is not a big addition to our baseline requirements for correctness. This all boils down to the fact that the benefits of Rust are not that compelling for context of type data. At the same time, Rust has costs, and the main cost here is complexity. Rust has a steep learning curve. Rust has a pretty high cognitive load, even if you are past the learning curve, if you know language pretty well. I know language pretty well, and for me it is still sometimes hard to read Rust code, because when you go to some fancy abstractions, you need to unravel a lot of language machinery, which is there for a good reason, to ensure memory safety, but still. For arts, simplicity is a core principle, and we really need to achieve that simplicity to fulfill the rest of this desiderata. So the fact that Zig manages to exceed expressivity of Rust using a fraction of language machinery, even if it doesn't achieve 100% memory safety, and maybe just 80% memory safety due to all the safety checks that Zig has, is actually extremely compelling for us. And on top of that simplicity, we do take this extra expressivity. We do take advantage of this extra expressivity. Specifically, we need to compile all the limits. We need to compute all the limits at comp time, which we do pervasively. And we also need to ensure that our data structures are exactly specified, that all the patterns are accounted for, that like, we don't have pointers where we should only have indexes and addresses and whatnot. And again, kind of like this expressivity, this ability to just like go and reflect on types compile time helps there a lot. And finally, this is like this thing that the big idea of the shape of the code is that we don't allocate after startup in Zig. That's kind of just idiomatic way how you write the code. In Rust, that would require kind of like swimming uphill and like battling the existing idioms of the language. Okay, so while summarizing, I realized that there is one more, again, important thing which I kind of forgot to tell about you, and that's the kind of one more aspect of like how Zig allows you for controlling, like, tighter control over layout of things than Rust, and that is what would be important. I guess like free set. Yeah, and that's aligned. It's actually kind of hugely important because, like, if you look at our code, like we care about alignment a lot. Like, for example, not message last message pool. So, for example, when we allocate messages, like, we want our like message to be aligned to the sector size on disk. So we could kind of like cleanly zero copy stuff from memory through direct I/O. And again, it just allows you to slap alignment to the pointer, and that makes it a very kind of like easy to just like care about alignment. Well, in Rust, kind of you can't really do this. Or kind of like in Rust, if you do some like struct foo, kind of like say that like it is aligned to something, but like this lives in the syntactic universe. Like you cannot actually like go and like compute this alignment from like some constant like we do here. That's like going to be changing. Again, this is not a fundamental limitation of Rust. This is like something which Rust hasn't implemented yet, simply because it's not very needed for a lot of different software. But again, like, in Zig you could just use them. So yeah, kind of like let's do like a very quick TLDR is that Zig is cool, Rust is cool. What matters is context. Context in Terminal is highly unusual, where the benefits brought by Rust are not that large, and the benefits which are brought by Zig are comparatively more important, and that's why Zig versus Rust. Okay, yeah, kind of like, yeah, sorry, I think it was kind of like super unstructured. I probably should have prepared like some more kind of like tree shape piece of things here and there, but I guess that's actually okay because, well, that's the idea here. That's kind of like unscripted. Just this is how it works, and I guess most important thing is what I told you at the beginning, that if you are watching this from the beginning, you kind of like already have better understanding of the context of technical, because what I'm like telling you here, where I'm like vigorously waving my hands, is not important. What important is kind of like actual like shape of the code we are looking at. What's important is that when you like open client sessions, you kind of like see how we document it here, and you kind of like it immediately clicks in your head that, hey, actually like it's going to be like hard to do in Rust. So yeah, I guess that is it, and see you next week. I'm not entirely sure right now what we're going to start looking at next week, but probably we are going to dive back deep into the source code and look at how our write-ahead log and checkpoint infrastructure works, and kind of like understand on kind of like more low level how Tailwind works. Okay, Thanks for watching and see you next week.